Lately, we've been working with quadratic equations like this, and under normal circumstances, we'll end up getting two solutions to that equation. But today, we're working with something unusual, and we're going to find situations where we either get no solution or maybe just one solution. Here's an example where I'm going to solve this quadratic equation using the square root method, and something weird's going to happen along the way. As I go through these steps and I'm trying to get the x squared by itself, I eventually get to the point where I need to square root the left-hand side and square root the right-hand side, which means I need to do a square root of -9, and go ahead and try that on your calculator. Kaboom! You can't square root a negative number. This is a sure sign to you that you have no solution. Anytime you end up square rooting a negative number, you will have no solution. So let's take a look at this equation. It's another quadratic equation. It's already in standard form. That's nice. So I'm going to go ahead and use the a, b, and the c and use the quadratic formula to solve that equation. Now as I'm going through here, I'm going to go through here kind of quickly. I plug in. I'm just minding my own business. I'm starting to simplify things. And as I'm simplifying, I eventually get to the same thing we just had. We've got ourselves a square root of a negative number. The 1 minus 16 gave me -15. Kaboom! You cannot square root a negative number, so you will have no solution. A quick side note about vocabulary. When you're working with the quadratic formula, inside the square root, the b squared minus 4ac, the vocabulary word for that, often used in the math circles, is the discriminant. So when the discriminant is negative, you can't square root a negative, you have no solution. So the previous examples I showed you have all involved square rooting and ending up trying to square root a negative number, and you can't square root a negative number, so you get no solution. But now let's focus a little bit on what happens when you want to solve by graphing. Here's a quadratic equation set equal to 0, so I'm allowed to graph it and find the x-intercepts, otherwise known as the roots or the zeros, and that's the answer to my equation. Some students would say that's the easiest graphing method available, or the easiest solving method available. But let's look at what happens if something gets a little bit weird with this. In this example, we've got a quadratic equation set equal to 0, so you'd say, hey, I'm going to graph that and find the intercepts. But when you graph it, here it is floating up here, and it never hits the x-axis. If there's no x-intercept, that means there's no roots, there's no zeros, there is no solution. It could even happen that you end up getting a graph that has just one intersection point on the x-axis. So here's another equation in standard form set equal to 0. You're going to graph it and look for the intercepts, but if there's only one intercept, that means there's only one solution. In this case, the graph vertex just barely touches the x-axis, but that's good enough to be an x-intercept. The last examples we have to go over of unusual solutions relate to when you have a system of equations and you're going to solve the system by graphing. As you know, when you have a system, go ahead and graph both equations, and the x values where they intersect is the solution to the system. So in this case, I know I have an x equals -3 and an x equals 4 for the solution. And since it's a system of equations, you need an answer for both x and y. And so when I look at these intersection points, I see the x-coordinate and the y-coordinate, x-coordinate and y-coordinate. That tells me the y value of the solution is 12. In this system, when you graph it, you just get one point of intersection. But that's okay, that just means you have one solution pair, the x equals -1 and the y equals 2, which is the x and the y of the point of intersection. And as you may have guessed by now, Here we have another system of equations, but when I graph it, I find no intersection. So very logically, if there's no intersection points, there is no solution.